Okay, so we're going to spend this time in the office hours here to get a little bit more help on the Chem 150 review, which includes a few more topics than the ones that I focused on very specifically last week. So one of these here is the heat of reaction, or delta H. And so you're asked to use Hess's law, which is basically a way of adding up reactions in order to get an overall reaction and the enthalpy change for that reaction for a particular reaction that's described here. So what's described is that we're going to use Hess's law to find the heat of reaction, or this is also known as the delta H of reaction, for the reaction where this is formed. So we're going to form black iron oxide, and this is going to be formed from iron and calcium carbonate. So let's write out an equation that would represent that. Okay, so that would be iron, just solid iron, and calcium carbonate, CaCO3, and these are going to be forming Fe3O4, which they call black iron oxide. Kind of a weird ionic compound here. But they give you the formula, so you didn't have to figure it out for yourself. So the question is, how would you add these reactions in such a way that you would get the overall equation here for that we're given? The iron plus the calcium carbonate is going to make the black iron oxide. Okay. And so let's kind of identify within these equations what are the important substances that are involved. It will be iron right here, calcium carbonate right here, and the iron, black iron oxide as they call it. Now there is one, what you're going to have to do is, in this first equation, what they did was they didn't mention everything that might be involved, all of the products and all of the reactants. So what we're really doing here is we're adding these two equations together, and I've kind of run out of room underneath. So I'll make a little bit more. And I'm going to get rid of this so that I can use this space down here. And you guys can do this on, just a normal piece of paper is fine. When we add these, what we're going to find is that we'll have other substances that are not just iron, calcium carbonate, and this so-called black iron oxide. But what does cancel here when we add these is we have calcium oxide coming out and calcium oxide going in. So when this is when produced, it will then be used up. So that's not going to appear in the final reaction here. So what our reaction will be is, as we see up here, the calcium carbonate, solid, that's from right here. We also have the iron from the second reaction. But for the products, we have more than just the black iron oxide, as they call it. We have a couple of other products, CO2 gas and solid calcium. And so this is the overall reaction that we want the delta H for. And it tells us to use the appendix in our text. And so we're going to have to find delta H of formations of each of these. And these are going to be in kilojoules per mole. Okay, so let's go ahead and look at where that is in the textbook. So if we're looking at the textbook here, let's see, brief context is probably what we want. we're looking for Appendix C, the the Appendix B, the standard thermodynamic values for selected substances. And this has the delta H's of formation here. Okay. So we're going to be using those right here. And it's delta H of products minus reactants. But let's get all of the values first. Now, one thing that's important for you to keep in mind is that delta H of formation, and we'll talk about this more when we get into the thermodynamics chapter kind of late into the course. The delta H of formation of any element in its standard state is 0. So if we were going to look this up, for example, for calcium right here, we see calcium is right down in here, and we see that the delta H of formation right here for calcium is 0. That's true for all elements in their standard states. So it's going to be 0 for the calcium. And it's also going to be 0 for the iron. We could look that up. If we go to a subsequent page here, look for the iron. We can see right there. For iron, the delta H of formation is 0. It's true for all elements in their standard states, like solid iodine here or hydrogen gas H2 here. That will become a big deal later on, nearer to the end of the class. Okay. And so now we're going to look up the delta H of formation values for some of the other things that we have here. So one of them is calcium carbonate right here. It's negative 1206.9 kilojoules per mole. Okay. For the CO2 gas, it's right here, negative 339.5. And then for the black iron oxide, that's going to be over here with iron. We have it right there. 1121, negative 1121 kilojoules per mole. Now, the way to get the delta H of the reaction is this way. Delta H of the reaction equals the delta at the sums, so that's indicated by this big Greek sigma. The delta H, the sum of the delta H of formation of the products times the coefficient in their balanced equations. So we'll call those A. Oops, I should put that inside. But anyway, for each one, I kind of put that in the wrong spot. Let me see if I can move this sigma a little bit. Oh. Okay, so we do sigma, I'll call it M, times the delta H of formation of the products minus the sum of N, these are the coefficients in the balanced equations, times the delta H of formation of the reactants, which I'll just call react. So now we can plug those things in there. So it's going to be the delta H of the reaction is going to be for products here. We'll add up. Well, actually, let's double check that this is balanced first before we continue. I didn't check that, but we have 1 calcium on both sides. We have 1 carbon on both sides. We have here iron. Here we have 3 irons, right? Here we only have 1. So we got to make sure that that's balanced. I hadn't balanced that yet. So we put a 3 right there. Now we do have an issue with the oxygen. So we may have to erase this later on. But the oxygen here, the problem is that we have 4 plus 2. We have 6 here, but we only have 3 on the left side. So we're going to have to balance this one here. And we're probably going to end up erasing a few things. So make sure you do this in pencil. If we put a 2 here, that would balance our oxygens. But then our calciums and our carbons are going to be off. So we're going to end up doing a little bit of erasing here. So we can see here, if we count our carbons, we got 2 here, but we've only got 1 here on the right. So if we put a 2 here, then that throws our oxygens off again. So this is actually quite a challenging equation to balance. At this point, we've got 4 here, 2 times 2 plus 4, 8 oxygens. But a big issue here is that we can only have a multiple of 3 oxygens, because on the left we have calcium carbonate. So for, let's say, for example, we erase this 2 and we put a 3, then we have 9 oxygens. So we have to see, is there a way, if we put a 3 here, would we have, to balance the carbons, would we have 9 oxygens? Well, no, we'll have 6 plus 4, we'll have 10. Okay, so we're going to keep escalating this number right now. So if we have a 4 here, that gives us 12 oxygens. If we have a 4 here, that gives us 8 plus 4, 12 oxygens. Okay, now we're balanced with these. Okay, and we can now balance our oxygens with the 3 here. So 3 on the right, 3 on the left, and we'll balance our calciums with a 4 over on the right. And so now we are balanced. And so we're going to find the delta H for this balanced equation. Questions so far before I continue?
Yes, Professor, I actually have a question. So what's the M after the sigma and then N after the sigma? What does it stand for?
The M and the N stand for the coefficients in the balanced equation. So for each of these, we have to multiply them by their coefficients in the balanced equation. And that's why I had to balance the equation first.
Oh, I see, I see. Thank you.
Mm-hmm. Other questions? I don't know what happened to my little video, my little video thing on the corner, but I don't see anybody. But I'm looking at the chat. Oh, it popped up again. That's weird. Oh, I guess it goes away if no one has video. Anthony, are you saying something? You're muted.
Yeah, if someone open the camera, you can see it, but because everybody's
Yeah, what happens is it only opens up if someone has a camera on, which
yes,
now I didn't know that.
I will leave my camera on, so you.
Oh, it doesn't matter. It kind of clears my space, but I was worried that you guys might be trying to like say something and I couldn't.
Oh yeah.
But yeah, if you don't want to have camera on, that's fine. Whatever you guys want.
I will leave it on so you can see. If it bother you, I close my camera because I see it's in the way.
Yeah, it does pop up on the side for me too and kind of covers things up. So it doesn't bother me if you turn the camera off. That's totally fine. As long as I can help you guys when you need it. So let's go ahead and continue now. And so we're going to do the products here. And so we'll have, whoops, there we go. For our black iron oxide, as they call it, we'll have 1 times negative 1121. 1 because I didn't write it, but there's a 1 here in the balanced equation. Plus, for the carbon dioxide, 4 times negative 339.5. And these are all kilojoules, by the way. I'm just not writing kilojoules to save space, but these are kilojoules per mole. And then we'll have 4 times 0. I'll just leave that off because 4 times 0 will be 0. And then we're going to subtract the sum of the delta H's of formation of the reactants times their coefficients. So it will be 4 times that for the calcium carbonate, which is negative 1206.9, and that is also in kilojoules. And then we have iron 3 times 0, that will just be 0. So I'll just leave that off so that everything can fit okay. And now I can calculate this out. So it will be 1121, and that's negative. And then it will be minus, because we have a negative here, 4 times 339.5. And then this will be a negative of a positive, so it will be plus 4 times 1206.9 equals, and we get a positive value. So delta H of the reaction is positive 2348. 2348.6, and the last sig fig is at the ones place because we added something where the last sig fig was at the ones place. This one was only good to the ones place. So our result's only good to the ones place. And then we can write our result as kilojoules or kilojoules per mole. When we get to the thermodynamics chapter, I'll be talking a lot about the per mole thing. A lot of times people will write this as just kilojoules and assume you understand that this is per mole. And sometimes they will include the per mole explicitly. But what this is saying when we say per mole is this. The way this translates is that if 4 moles of calcium carbonate react in this reaction, then 2048.6 kilojoules will be absorbed. And this will be absorbed because this is a positive delta H. This indicates an endothermic reaction. You must put energy in to make it happen. Every time this 1 mole of iron, of the black iron oxide is produced, 2,348.6 kilojoules must be absorbed by the reaction. Every time 4 moles of carbon dioxide are produced, this much energy is absorbed. And so the answer to the question here is the process 9 exothermic or endothermic? It has a positive delta H, so this process is endothermic. And you know, because delta H of reaction is positive.
Sir, I was wondering if the experiment A is due, it's like, do you need us to do everything in it? Because there's a lot of stuff.
There's a lot of stuff. It's a big review. I will tell you that I'll be gentle with the way I grade it. And, you know, there's lots of time for you to ask questions if you get stuck. I won't demand it. This is generally true for most of your homework. I won't demand perfection. I will look to see, did you make a solid attempt at every problem? Okay. That's what I'm looking for. I do want you to make a solid attempt at every problem and be mostly right. At least have taken the time to ask me if you were uncertain at an office hours or something.
Okay, sounds good. I have a question about the homework, number 4. I watched the video several times, and I don't seem to have like a similar question to it.
Okay. So yeah, so I gave you a few examples, but there are lots of possible things that could, you know, possible ways these questions could be asked. So all of these, this is about the kinetics, how fast that the reaction goes, right?
Actually, my problem it's not the way you solve it. It's the way to verify what to use. You know what I mean? Like what to do here.
There's one equation, right? One equation for the kinetics, how fast these go. And it's this equation right here. That's the equation that we're going to be using. And the related equation for half-life, which we won't really need, but the other equation that we derived from this was this. if we were given the half-life, this is how we could find the rate constant. But we weren't given the half-life this time. So this equation will not apply. What we are given is the percent that is remaining, okay? So we could turn that to a ratio here, and we can use that to figure out K. Now what we want is the decay constant, which is indicated by K here. What we want is K. So we should solve for K. So we're going to use our algebra skills to do that. We're going to divide this side by negative T. And we're also going to divide this side by negative T so that we can get K. So I did do a problem like this, but I didn't solve for every possible variable. I didn't solve for K.
I'm sorry, Professor. How did you know that we need to solve for K? Like, because I don't get the question. Like,
oh, it's because you're asked what is the decay constant, and the decay constant is K. That's what K represents in this equation. So since you're asked what is the decay constant, you want to solve this for K. Anytime you're asked about how much time it takes for a process, radioactive process to happen, this is the equation that you're going to use.
okay, so can you tell us what is what? Because what is NT, what is NO, what is T?
Mm-hmm.
So tell us, like, okay.
T is time. So the time that has passed. This is going to be T, okay, right here. This is how much the fraction of atoms that are disintegrating in this period of time. Okay, so basically what this is saying is that the amount you have at the beginning minus the initial amount over the amount you had at the beginning, that is this number right here. It's the amount you started with minus what you lost, right? So it's the amount that you lost, which is the amount that you started with minus the amount that you have after a certain time has passed. Okay.
So this is the total
basically an easier way to say this is this is 1 minus NT over N0. That's the easier way to say it. So it's what we start with is 100% or 1, right? And what we have at the end is basically this is the ratio of the amount we had at time T minus over the amount we started with. So what we want to do basically is we want to get this. We want this. We want to know what fraction of our atoms are left. That's what I had you solve for in the example problem that I did. We solved for this. What we're going to do is we're going to solve, well, we've got this. Now we're given this, basically. We just need to take 1 minus this. Okay, so let me finish solving for K here, and then we're going to plug this in, okay?
Okay.
So I'm solving for K. I'm going to cancel the negatives here and cancel the T's, and that leaves me just K. So K equals -1 over T times the natural log of the initial amount over, or the amount we have at time T over the initial amount. The problem is we were almost given that, but not quite given that. We were given 1 minus that, okay? So let's look at this and let's convert it to a fraction now, not a percentage. So we have 2.8 times 10 to the minus 10%. And we're going to instead make this into a decimal. So we're going to divide by 100%. That gets rid of percent. And now we have a decimal, this in decimal form. It's 2.8 times 10 to the minus 8.
12?
Or 12, yeah, so sorry. I went the wrong way. So this is the fraction. This is what is the amount that was used up. So the amount that wasn't used up, or this, is going to be NT over N0 is going to be all of it minus what was used up, 2.8 times 10 to the minus 12. And that is what we're going to plug in here. Admittedly, yes, this is harder than the question that I showed you in the chapter, but it operates off the same principles.
Yeah, but I didn't know that how to change the percentage. I know how to change your percentage, but I don't know I need to change the percentage. And I don't know that's 1 minus the percentage is the NT over NO.
Yeah, this is about reading the problem, right? And understanding what it's saying. So a lot of the ones that I told you to start with in the textbook too, like the example problems, they're like this, but a bit simpler. So I'm giving you a bit of a challenge here. You have to read the question and think about what it says. What it says is this many will disintegrate. So if we're talking about the fraction that are left, that is 1 minus this, right? That's what's left. 1 is 100%, all of it, minus this right here, what we lost, which was this. So that's going to be our NT over N0. And our time is 1 year. So now, I won't give you something this hard in the quiz, I promise. But on the homework, I do make them a little bit tougher. I'd rather you see a hard one on the homework and say that was hard than to see a hard one on a test and say, oh no, I just flunked, right? So here we're going to get 1 over divided by 1 year, okay? Because 1 year was the amount of time, T. That went right in there.
Yeah.
Okay. And now we're going to have our NT over N0 is 1 minus 2.8 times 10 to the minus 12. So we're going to end up with a fairly, a number that's quite close to 1 actually. So now let's punch that into our calculator. These are all 1s. So your unit is going to be.
You get rid of the natural log?
What's the natural log? Oh yeah, the natural log, sorry. Boom. So we're going to have the negative of is 1 over 1. So this will be natural log of 1 minus 2.8 times 10 to the minus 12. And the units are going to be 1 over years, or years to the minus 1 power, which is 1 over years. And now let's put this in to our calculator. 1 minus 2.8. Use your EE or your EXP, negative 12. And we get 0.999972. You could put this in scientific notation too. And then we're going to take the natural log of that. Natural log, that gives us a negative. Okay. And let's write this with 2 sig figs now. So this is, let me make this a little bigger in case you can't see it. Right here, it is a negative of a negative, so the negatives go away. 2.8 times 10 to the minus 12 inverse years. And that is K. That is your constant. Years. Okay.
I did something wrong. You did 1 over 1 and negative 1 over 1 in the calculator, right?
Yeah, it's just 1, right?
Okay, so.
And the unit here, year, is 1 over year. So that is year to the minus 1 power. That's what 1 over year. That's another way of writing that. So you'll see your book
Okay.
do that a lot.
But when I put the natural log of 1 minus 2.8 times 10 to the negative 12, I got a different answer.
You got it. So 1 minus, let's do the first part. 1 minus 2.8 EE minus 12. You should get this.
Okay, just give me a sec. Yes, I got that.
Okay. Then take the natural log of it.
I got a different answer. I got 0.000003.
Yeah, just turn your calculator so it says scientific notation. You got 0.000003. This is the 3 right here. It's just you can't see the next digit because it's off the side of your calculator.
Oh, okay, I got it. Okay.
Yeah, so sometimes it's useful to make your calculator display in scientific notation in situations like this. So this is admittedly a tough one. Maybe I should have saved this for problem number, 6 or something.
Yeah.
Other questions? Did I lose anybody
Even,
somewhere in
even
here?
5 and 6 is very hard too. But I got the idea now. Like if
They're
I
all going to
take
use this equation. They're all about kinetics. So it says when you see how long or half-life or whatever, what you're using is this one.
and if it's a half-life, we are using the time 1/2 equal the.
Right. If you're given the half-life, you may need the K. So you have the half-life equals natural log of 2 over K, or equivalently, if you need to get the K is natural log of 2 over the half-life. So like right here, for example, the K is the natural log of 2 over the half-life 1.60 times 10 to the 3rd years. So the rate constant there would be take 2, take the natural log of that, you get 0.6931 about, and then divide by 1.6 times 10 to the 3rd. So you get, for the K there, the decay constant, it's 4.33.
332 times 10 to the negative 4.
All right. That is, and the unit is year to the -1. Don't forget the unit, 1 over year.
So we have to change year to hour, right? Because it's asked for how many hours will it take?
Yeah, so in the end, you're going to get an answer that is in years, right? If you use the year to the -1. So you'll want to change that to hours. So here, this one, this is going to be the N0. This is how much you start with. This is the NT. Now the N stands for the number of atoms, but grams is directly proportional to that. So we can use that instead. That's fine. And what we want is how many hours. So what we want to figure out is the time. So to get the time, we're going to have to divide both sides by -K. So the negative cancels, the K cancels, and we get the time equals -1 over K times the natural log of NT over N0. This is going to be -1 over 4.33 times 10 to the -4 times the natural log of 0.185 grams over, yeah, because that's how much is left, and That's divided by the amount that you started with,
2.50.
2.50 grams. And this is a year, this right here, I forgot the unit, it's year to the -1. Don't forget the unit because you might forget that you're still in years. After you calculate this, you'll have to convert the years to hours since it was asked for in hours. So I can do 0.185 divide by 2.5. So that's inside the natural log there. I get 0.074. Then I hit the natural log button, take the natural log of it. I get negative 2.6. And then I divide by negative 4. Let's divide by negative 4.33 times 10 to the -4. Yeah. And I get about 6,013. And the units are 1 over years. So your units are 1 over year to the -1, or year to the -1 means 1 over year. So that means that's year. So these are going to be units of years. And convert those to hours. The reason why I asked you for hours here was because if you forgot that you were working in years, you'll forget to convert to hours at the end. That's why it's really important to keep your unit. Does anyone want to ask a question about one of those steps? Either one of these. Did I lose someone at a certain step here?
Dr. L,
Yeah.
I was wondering, where did you got the 4.33? I know you divided by 1.6, but what is it said, natural log of 2?
Yeah, natural log of 2. So that the half-life, and if you watch, when you watch the video, you'll see I kind of derived this for you, where it comes from. It comes from this equation. But a lot of times people memorize this, especially when we go into chapter 16 in the next chapter. This will be really handy for you. If someone talks about half-life, what you really want is the decay constant or the rate constant. And so you can get that from the half-life directly if you have this equation. You don't have to memorize it. I don't always have it memorized, but I know I can get it. The way I got it was deriving it from here. But yeah, I did natural log of 2 divided by the half-life. And the half-life was given to you right here. It says the half-life is 1.6 times 10 to the 3rd years. And so that's why I put it in right there. And that's how I got the rate constant. That's the K.
Got it. Thank you.
And we'll be talking about this in more detail in the next chapter. This is kind of your first exposure to this formula and using it. Anyone want to follow up more on one of these 2 questions?
Last night I was having a hard time with questions 6 and 7. I didn't really know where to start from.
6 and 7. So
Yeah.
for 6, I ask you to calculate the binding energy per nucleon.
Correct.
Okay. There's a couple of ways of doing this. What is the thing that I really need to calculate to be able to do this, though? What will tell us how much energy was made? Looks like this.
We have
What was the name we call that?
the mass, the delta, the change in mass.
Yeah, the change in mass, the mass defect, as they call it, right? The difference between the mass of the lead-206 atom and its individual protons and neutrons. So when the protons and the neutrons come together, they lose mass. And that mass is what contributes to the binding energy of the nucleus. So if we're looking at the slides here, the problem that I did, so just to kind of go back and show you similar problems that I did, the problem that was kind of like what we did here, but the reverse of it, what we did in problem 4 was this one, where I give you the half-life and I ask you what % of the sample remains. But in the problem I gave you on the number 4 on the homework was, I gave you the amount of the sample that remains and asked you for the amount of time that passed. So it was like this question, but kind of the reverse of it. For this one, this question I'm asking you is very much like this question that I showed you. So here we ask for the binding energy of iron 56 per nucleon. And so you need to calculate the mass difference, the mass defect, in order to determine that. And a shortcut that we will use is this shortcut we derived here, where we're gonna, instead of using E equals MC squared, we can use that 1 AMU translates to 931.5 mega electron volts. That's what will be useful here. And if we look at the homework, back at the homework, I do think I put the mass of the proton and the neutron. I didn't put the shortcut up there, but we do have the mass of the proton and the mass of the neutron. So we'll need these.
Yeah, I totally forgot about this. I thought that I'm missing something, but yeah.
So here's the mass of the proton, the mass of the neutron. That's what you needed. And also useful as a shortcut is this. 1 AMU will translate to a binding energy of 931.5 mega electron volts. Okay, so we need to find the mass defect, and so that's going to be the mass of the lead-206, or sorry, the mass of the protons and the neutrons separately. So the mass of all the protons plus the mass of all the neutrons, all of them, I'll say all here, minus the mass of the lead-206 together. That's going to be our mass defect. And so the mass of the, and we need to figure out how many protons and neutrons are in this thing. So we've got lead-206, PB. So we should look on our periodic table and see what is the, yeah. So right here, element 82 is lead, so that's the atomic number. So we'll write it in here, 82. So that means we have 82 protons, and our neutrons are going to be 206 minus 82. So our neutrons are going to be 124 neutrons. And we have the mass of the lead, it's given, the lead atom, this particular lead atom. Okay, so we will do then 82 times the mass of the proton, 1.00727647 AMUs. We're going to add to that the mass of the neutrons. There's 124 of them. 1.008664,904 AMUs. And we're going to add those together, and we're going to subtract from that the mass of the lead atom, which was given in the problem right here. And so that's going to be minus 205.974440 AMUs. Okay. So 82 times 1.0072766470 plus 124, and you guys should be punching this with me. Make sure you can do this. 8664904 minus 205.974440.
I got the same number.
You got the same? Now let's make sure we know the right number of sig figs for this too. So I'm going to write out what came out of the calculator. 1.69666678636 AMUs. Now let's look at the place values for these. So the place value here is like 1 for the proton. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 past the decimal. Also 9 past the decimal for the neutron, but for the lead atom, it's only 6 past the decimal. So when we subtract, we can only, because this one here is 6 past the decimal, we can only trust this to 6 past the decimal, where the 8 is. We should write our answer with 7 sig figs. And then what we're going to do is now convert this to mega electron. This is for all of the nucleons. Let's just get it per nucleon first, or we could do that at the end. Either way, it doesn't matter. You can convert to mega electron volts first, then divide by the number of nucleons. Let's do that. So for the whole atom, it was 1.696679. I'm just going to round it right there. AMUs, and it was 931.5 mega electron volts per AMU. That gives us mega electron volts. So we'll do times 931.5. And at this point, because we used a limited conversion factor, I guess we only have 4. We could have gotten a better conversion factor here, but this is fine. We're going to say 158, we'll round off to 0, 1.580 mega electron volts. And then we're going to divide that by the number of nucleons, which is 206 protons and neutrons. So divide by 206, and we get 7.672. Mega electron volts per nucleon.
I get a different number because
Because of rounding?
I did 1580, not the whole number.
Ah, right. That's okay, as long as it's the last sig fig. You know, there can be a little bit of variation in the last sig fig. You get a 1 or something here, or 3 in the last one.
I get actually I got like 7.6699. So
7 point. So basically 7.67, right? Yeah, it's close enough.
okay.
So when you guys enter answers into the like quiz or test, for example, there's always going to be a range too, a little bit of a range, plus or minus so many percent, because there can always be a little bit of rounding errors. Because like for me, when I wrote it rounded off, but then I just kept going in my calculator, so it was carrying a bunch of digits.
Mm-hmm.
That can change the value of the answer a little bit on the last sig fig. Maybe.
So it's not going to be multiple choice. It would be writing a number, right?
Well, there'll be a mix. So just like on your last quiz, the last one was you put in the number. For this quiz, I had you put in the number. And then for your exams, there'll be some multiple choice, some you type in the number. And for the exam, for the ones you type in the number, I'll also have you upload me your work to show me what you wrote, like the homeworks.
Okay.
And number 7 is a similar thing. So
I think it's similar to the first problem you did.
Yeah, you just need to get the delta M. It's a little bit more complicated because there's more stuff here, but you can get the mass of the neutron from the information in the beginning. Take the mass of the products, subtract out the mass of the reactants, you'll get the difference in mass, and convert that to energy. One thing you might need for this one is if you're going to do energy, you'll want to convert the electron volts to joules if you use that shortcut. Or you could just convert the AMUs to kilograms and use E equals MC squared. Both of those ways are fine. But it's the same type of thing. You're going to get the delta M. That'll be in AMUs. Then you can convert that to electron volts, or you could use E equals MC squared. If you use E equals MC squared, so that one we used last time, 1 mega electron volt equals 931.5. 931.5, 1 AMU rather, is 931.5 mega electron volts. That is just a shortcut to using E equals MC squared. If you use E equals MC squared, which is pretty good here because it'll get you straight to joules, but you could convert mega electron volts to joules. Or mega electron volts is just another way of saying energy. You could just leave it like that. I didn't ask you to get joules. But here we've got E, which is energy. That is in joules. Mass should be in kilograms. And C is in meters per second, but it's squared. So a joule is equal to a kilograms times a meter squared over a second squared. That's what a joule is. So these units work out to joules. Alternatively, I've got the conversion factor between electron volts and joules here. Now, one thing to note, and I did do a problem like this also in the lecture. For this one, it asks you per mole. So this energy that when you calculate this, this is for one of these. This is the energy for one, not for a mole. So it'd be, if this would be the energy you calculate here or calculate right here is for one hydrogen 3 reacting with one hydrogen 2, making one helium 4 and one neutron. If you want a mole of these, you're going to have to multiply the energy times 6.02 times 10 to the 23.
This is the Avogadro number, right?
The Avogadro's number, yeah. The way where I showed you to do that was right here. So this problem is very much like this one that I showed you in the lecture. So I think at this point, actually, we've covered most of the homework now between the last office hours and this one.
Yeah.
Now, what you guys will probably need help with next time, and what I encourage you guys to do before the next office hour is to take a crack at, or to start working on this Chem 150 review. So I covered the big topics here on the Chem 150 review, like, how to do some stoichiometry using molarities right here. Or how to write the product of a precipitation reaction like this one and determine what will be the precipitate. Or to, let's see, to write a neutralization reaction like this. Now, what I didn't go into as much detail on was oxidation and reduction, okay? So I'll give you guys what I'll do. Basically, I haven't done it yet, but if you guys are struggling, I'll just give you some references to the textbook where you can kind of look over things. I'll tell you that I covered, what's in practice 2 more, and what's in these questions more, topic 2. The last ones, they ask you to do some oxidation reduction. So practice 4, I didn't cover as in depth. I may need to make an extra video of that for you guys, but do your best. And I'll point to you in the book where it is. It's in the part about oxidation reduction reactions, the same chapter where we talked about all of this stuff. It's all in chapter 4 of this. Then this stuff is about the combination of these things, molarities, and this topic 3, we covered this quite extensively, moles, limiting reactant, solution concentrations. So topic 3, this is what I focused a lot on last week. I didn't focus so much on delta H reactions. So if you want to look at what we did here for this delta H, you can come back and look at this. When it comes to the Born-Haber cycle, you may want to look that up in your index. It's a very short portion of your book where they talk about that, but it includes a number of definitions. For this question, do your best. We're not really going to do a lot in regards to Born-Haber process in this class, but you do want to understand what these terms mean, like ionization energy and heat of formation and so forth. So that's why I have you do this. Look back at that part of the textbook. I'll give you page numbers too over the weekend, guys. You still have over a week to finish this, but there'll be some other things, of course, to do next week. So you want to get started early. We didn't focus too much on drawing Lewis structures here, but if you need a review on that, let me know. Again, I can point you to the right textbook pages. When I did the review last week, I tried to hit the high points, the most important parts. But of course, you learned a lot in Chem 150, and I can't cover it all in, a couple of lectures. So yeah, this one's just drawing a graph, basically. These ones here, these are more solution stoichiometry problems like I covered last week. This one is a serial dilution like I covered last week. And then these are figure out how many protons, neutrons, and electrons. Pretty straightforward. We've been doing some of that this week. And then this is just a little bit more detail about quantum numbers and the electron configurations. So that's something you may want to review. If you guys get stuck on a particular problem, you can let me know and I'll help you with it. Again, for this one, I'm not going to look for perfections here on this. I know a lot of these questions are really tough, but I'm going to look for an effort to review what you knew before. That's what I'm looking for when you do this. And of course, there's not a lot of room on this paper. You can turn this in on a white piece of paper written out.
I was wondering, where do we turn it in?
I haven't put up the place to turn it in yet because it's not due this week. It's due next week.
Oh,
So
okay.
you'll see that pop up next
Better.
week. What will be due for lab is two things. It will be this experiment A, which you started on this week, and it will be experiment B, which is about graphing using Excel. And I'll be doing a dedicated lecture to that next week before you do the assignment.
Awesome.
For next week's assignment too, it's you will need Microsoft Excel. So I suggested to you guys to download that the first week. But if you haven't downloaded it yet, definitely you want to go and download Microsoft Excel if you haven't already. And again, this is free. You don't want to use the online one. Trust me, you don't want to use the online one. It's not very good.
I wasn't able to get it for some reason. It won't let me.
You should be able to go to student resources here. I did have students download it last semester. You go to Office 365, and you should be able to log in using.
Yeah, when I log in, it doesn't I don't know. It's something weird. I can email you the PDF of what it shows me.
Yeah.
If you're
Mohammed,
having,
I will help you when we meet in Zoom. I will help you with that.
Oh, okay.
if you need help too, there's the campus help desk. You should be able to log in using your campus information.
Yeah, I sent them an email and they ignore me totally.
They ignored you?
Yeah.
Okay, maybe I should make a video about this. I need to log out and log back in so I can show you guys. But you should be able to just log in using your credentials from the school. The same, email, password. You use your student email account and your password. And then you click here and choose install Office 365 apps. Because if you use the one Excel online, it doesn't have all the features of the one you download. It's not nearly as nice and it looks different kind of. So I really highly recommend downloading using the downloaded version. So they didn't, help desk hasn't been responsive, huh?
Yeah.
Man.
Professor, I have a quick question. Where is this record, the record we just did in office hour? Will you post it or?
I will post it, but it takes some time because when I record it through Zoom, it has to go through the process of like getting it ready. And then when it's done, I download it and then I upload it to YouTube. And then it takes YouTube a little bit of time to process. So whenever I record office hours, you can expect it to be there no later than the next day. But it does take like at least a few hours.
Okay.
So it depends on what I have to do in the meantime, but I do keep an eye on it and try to upload it as soon as I can.
Okay, thank you.
So for you guys, that's about wraps up my office hours for today. I did schedule an office hour 3 to 4 for one of my other classes after our office hour. So I've got to move on to Chem 101 material now. I've got a few of my Chem 101 students here. And so I'm going to start answering my Chem 101 students' questions at this point instead of Chem 151 questions. But if you guys have further questions, let me know and just send me an email and also we can arrange office hours from time to time. Try to make it, if you could, more during the day. We did do that 8 p.m. one, which wasn't too bad, but it's a little late for me. I know it's normal time, study time for you guys. It's a little late for me. I like to do them more in the middle of the day. But of course, you guys already know now, I'm pretty responsive and can try to be there for you when you need it. Not all the time, but and most of the time I can. Just let me know. Communicate with me. Okay? All right.
Thank you.
Bye.
You're welcome. I'll see you later. Chem
Thank you.
151
Bye.
students. Bye. See ya. And now I can help the newly incoming Chem 101 students.
Hi, Professor.
Hi. So how are you guys doing today?
Good, thank you. How are you?
I'm doing okay. Just trying to do a few extra helping sessions here when I can for you guys. Okay, so let me shift gears over to Chem 101 mode. Okay, and I assume there will be questions about the homework. So I will bring the homework up. Okay, I'll close this. And I'll bring up my slides as well. Where can you find a good conversion sheet? Okay, so for conversions, the only ones that you will need that I will not provide to you with the problem will be, whoops, I can close that one. Okay, the only ones you will need very regularly that I won't provide in the problems are these ones. The ones that are highlighted in the orange here, I want you guys to have those up here, okay? What those mean should be up here. So you should be able to remember that kilometer means 1,000 meters, for example, or 1,000 milliliters are in a liter. That's all related to this here. Those you want in your head. The rest, if you need them, I'll give them to you in the problem, okay? So you won't have to go and look them up. If you want some conversion sheets, I'm sure there's all kinds of, sheets that summarize a bunch of different types of conversions. However, if you need them in the problem, I will give them to you. You should not be memorizing any that are not these ones right here, but these ones you do have to memorize. I don't make you memorize the other metric prefixes, micro, nano, pico, or mega, giga. You've probably heard these before, like megabytes, gigabytes, right? In computers, when you're talking about really big things, we store a lot of information. So you usually hear these in terms of computers. Micro, you hear these in terms of computers too, like your computer might be made with a 12 nanometer transistors. That's very small. They're very small. However, I'll leave that for later classes for you to memorize. For this class, I want these ones memorized right here. And then for the rest of them, I'll give them to you. Kind of like I do on the problems in the slides. So when we do conversions like this conversion right here, when we do this conversion, I give you the relationship between inches and centimeters. The only ones I won't give you are the relationships between metric units themselves. So I won't tell you, for example, there's 1,000 milligrams in a gram, like right here. These ones, notice in this problem, I didn't give you that 1 gram is 1,000 milligrams or that 1 kilogram is 1,000 grams. I expect you to have that memorized here. So, all right. Also, some people have been asking me to record these, so I should make sure to record it just so that I have it later. So I'm going to record these. Oh, I need to stop the recording. Okay.